Good evening, everyone, and welcome all to week 10 of the problem solving session for the NPTEL course Dynamical System and Control. In the last week, we discussed about controller and observer design for linear dynamical systems. Now, in this session, we will see how we can give guarantee on the stability of a system using Lyapunov theorem for a non-linear dynamical system. And then also we will see a bit about how to design an optimal control for considering minimization of a cost function. So let's get started. Let's recall few of the important concepts related to Lyapunov stability. But before that, let's understand one comparison function which is often used in Lyapunov analysis for determining the stability of a system. So the comparison function that we need in this course is the class K function. First, let's see its definition, then we will while solving problems, we will take some questions on determining whether the function is of class K or not. So the definition of a class K function is like the function, let's suppose we call a function as phi, whose argument is r. So this function belongs to the class K function if and only if the function phi is continuously differentiable. So we call it continuously differentiable over a domain rho, and it gives a positive value. So the function is defined on the domain 0 to rho, and which gives positive values, and it is 0 at 0, and the function over the argument r is strictly increasing. So it is strictly increasing in the argument r. Now why we need this class K function? So this class K function is used basically in determining the Lyapunov functions, and in order to give guarantee on its positive definiteness when we have a time varying dynamical system or a non-linear function, then this class of function is used. Now in the earlier sessions we have already seen the Lyapunov theorem, various discussions on positive definiteness and negative definiteness of a function. So now let's quickly see the Lyapunov theorem for stability. So how can we give guarantee that the given dynamical system with its trivial solution, that is we are interested in its equilibrium point. So we want to analyze whether that equilibrium point, the system about its equilibrium point, is stable or not. So for that, Lyapunov theorem says that if there exists a positive definite function obviously we need to define some inequalities on the Lyapunov function. That's why the Lyapunov function should be scalar. So if there exists a positive definite scalar function, and we generally call it as V, defined over the state x, so it must be continuous and differentiable, and first we will consider the local result. So we are defining it over the neighborhood B row, and it maps to positive values such that its derivative along the system trajectories is less than equal to 0 in the neighborhood B row. Then we call the trivial solution or the equilibrium point of system of any nonlinear system x dot equals to fx. That is, we are interested in the equilibrium. So we started with a positive definite function. We defined it over a domain, or we are interested in the domain B row, which maps to real positive numbers. And if its derivative in that neighborhood, that is around the equilibrium point, is negative semi-definite, so here is less than equal to 0, that is, if it is negative semi-definite, then the trivial solution, that is nothing but the equilibrium point, so here we are considering it as 0, is stable. And the other condition can be quickly inferred from here is that if we started with same positive definite scalar Lyapunov function, and if the derivative along the trajectory is explicitly less than 0, or sorry, um, then the system is asymptotically stable. And if the derivative is greater than 0, or if it is positive definite means if it is greater than 0, then the system will be unstable. So these theorems basically covers the analysis of a nonlinear dynamical system of the form x dot equals to fx. So it is a time invariant system. Now, how to generalize the Lyapunov theorem for a nonlinear time varying system? So for that, we need to first analyze or see how can we define a positive definite function when we have time also as the argument. So for that, we modify the definition of positive definite functions. So when v is time varying, means it depends on state x as well as on time t. So in that case, v will be called positive definite. So v will be positive definite. So obviously we define it on the interval t to infinity for the time, and we are interested in the neighborhood b row. So this function v is positive definite for the time varying case, ed for positive definite, if the Lyapunov function at x equals to 0 is 0, and that should be satisfied for all t greater than equal to t naught, any initial time if we are considering. So at x equals to 0, this Lyapunov function should be 0 for all time, and there exists class K function, we call it phi, such that the Lyapunov function V is always greater than equal to a class K function defined on the norm of the state X on which we are analyzing our Lyapunov function, and this should be satisfied for all t and state X from initial time. Obviously we can go up to infinity, and we are interested in the neighborhood, so 0. So this is how we define the positive definite function or the positive definite Lyapunov function for the case of nonlinear time varying system. Now this is not the only thing that we need. We also need a function which we call as a decrescent function. So what is a decrescent function? It is similar to positive definite function only, but with a flipped inequality. So we call the Lyapunov function V, which we are defining on the interval t0 to infinity over the domain 0, and we call it to be decrescent if and only if the first condition that we need, that it should be 0 at 0, obviously for all t, and there exists a function psi of class K such that the Lyapunov function V is less than equal to that class K function with the function of the norm of the state obviously for Tx belonging to 0. So now we have these supporting functions. So using these we can define the theorem for stability using Lyapunov functions. So now if there exists, so here we are considering a time varying system, a nonlinear time varying system of the form x dot equals to f of t comma x. So if there exists, for such systems, if there exists a positive definite scalar Lyapunov function Vtx, so let's also define its domain. So it is defined on t0 to infinity, and it should be continuously differentiable 0, and it maps to, so let's write it clearly, positively scalar function Vtx, and this Vtx belongs to continuously differentiable defined on the domain T, and neighborhood 0 maps to R plus such that this V dot derivative of is less than equal to 0 in the domain on the interval and in the domain 0. Then we call the solution to be, the trivial solution to be stable. And for asymptotic stability, we need two conditions. The first condition is that if there exists a positive definite as well as a decrescent function, so we had already seen the definitions of both positive definite and decrescent function for the time varying case. So if there exists a positive definite and decrescent function v, so let's write out the domain, and such that the derivative is obviously less than 0 only on the interested domain, then the trivial solution is asymptotically stable. Alright, so this covers the Lyapunov theorem for nonlinear time invariant as well as nonlinear time varying systems. We will also see problems, then these things become clear on how to define a positive definite Lyapunov function, and for both time invariant and time varying systems. Then the another thing that is discussed is on the optimal control design. So for optimal control, we should know few things. The first is the condition of optimality. But before that, uh, we should understand when to call we must understand how to define the optimum of a functional. The function is nothing but a function of function. So let's say we have the cost function, something like x square dx, or anything, it could be anything, x square plus u square, something like this. Something like this. So for such type of functionals, when can we say that we have the optimal of a functional? So for that there is one logical definition. So a functional j, which is nothing but the cost function that we generally use in designing the optimal control. So a functional j is said to have a relative optimum at x star. So why we are calling it relative optimum? Because we are considering only a neighborhood of some point of interest. So we are analyzing our functional over that domain, because sometimes what happens, that is not the only optimal of the functional. There may exist some other optimal point in other neighborhood, so that may not be unique. So we often call it the relative optimum at x star if there is a positive constant c such that for all functions x in some domain, let's call that domain as omega, which satisfy So we are interested in the epsilon neighborhood of point of interest x star, and we want to know if there occurs a relative optimum at x star or not for the functional j. So we have defined the neighborhood around x star of width epsilon, and we call that x star to be relative optimum if the increment of j has the same sign. Obviously we can understand it with a very simple example. Suppose that we have some scalar function of this form. Now we want to know whether if this point x star is a relative, this function j has a relative optimum at x star or not. So we can evaluate our j around the neighborhood. So let's consider this neighborhood of epsilon width. Now when we analyze this system over here and here, so if I find j of x star plus delta x minus j of x star, and if I also evaluate j of x star minus delta x minus of j x star, what should be the sign of this increment? So since this value is less than of this value, so it is less than 0, and here also it is less than 0, means the increment of j has the same sign. What about this point? If we see this point over here, or let's say this minima point, if we have a relative optimum over here, over this point x star, then we can evaluate the neighborhood, the increment. If we see that, in that case we have j of x star plus delta x minus j of x star, so it should be greater than 0 on both the side if we evaluate. So it is greater than 0, so means the increment has the same sign. So if that is the case, then we have relative optimum at x star, and that we have analyzed by checking the sign of the increment of j. Now if we have the optimum, then the minima can be defined as, so that optimum will be minima if this delta j. So for minima we have seen that the increment is positive. So for minima we have greater than equal to 0, and we have a maxima if we have just the opposite of sign. So delta j is less than equal to 0. Now this is the definition for this is a condition for optimum for a point x star to be a relative optimum for the functional j. Now is there any way that we can give guarantee that that optimal will exist? So for that we have a necessary condition. Condition of optimality, we can say, and what it says that for a point x star to be a candidate for an optimum, its first variation must be 0, or in other way its gradient should be 0. So if the first variation of j must be 0 at that point x star, so the variation of j means delta j at x star should be 0 for all admissible values of delta xt. Now let's start with an optimal control problem. Suppose we need to find the optimal function x star of t which optimize the functional j, and we can write j as some generalized function f of xt, x dot t, and dt. So we say that we need to find the optimal function x star for this functional and we also need to satisfy these boundary conditions. So the boundary conditions are that the initial condition should be satisfied, the final condition, that is at some finite time we should reach the final state value x of f, and also the variations of states at t naught, because these are fixed, so its variation at the initial time and final time is also 0. So these conditions we need to satisfy, and then we need to find the optimal function x star which optimizes this functional j. So that the solution for such a problem is given by the very famous Euler-Lagrange equation, which is given as dou f by dou x minus d by dt dou f by dou x dot equal to 0. So this gives the necessary condition for optimum. So for such problems we need to solve this Euler equation. So this is called Euler equation, which gives us the necessary condition for optimum. Now if such function need to be optimized with these boundary condition, and also if we need to satisfy the dynamics also. So suppose the dynamics is governed something like xt, where x and x dot are vectors, it can be scalars also. If it satisfies some dynamical equation, because the states are constrained to move via some differential equation, so we need to optimize this cost function with the constraint that the state should evolve as per the dynamical equation of the system and with these boundary conditions. So when we have this constrained problem, we can convert this constrained problem to the unconstrained problem by defining the Lagrangian. So we define the Lagrangian L, which is obviously function of state xt, x dot t, and we introduced a variable lambda which we called as the Lagrange multiplier, and obviously it can be a function of time t also. So we need to transform the constraint problem to unconstrained problem. For that, we, instead of the functional functional j for and the Euler equation that we were evaluating for f, we define the Lagrangian, which is the same as that integrand and plus the Lagrange multiplier. So for n dimensional system, this will be of n dimension. So we have lambda 1, lambda 2 up to lambda n. So that's why we write it as transpose and into the constraint, that is nothing but the dynamical equation of the system. And now when we define this Lagrangian, we just have to enforce this Euler equation over this Lagrangian instead of the function f. Okay, this is how we solve a constraint problem using this Lagrangian that convert this constraint to unconstrained, and then we enforce the Euler's equation to find the optimal function x star. Or if it is a control problem, we can find the optimal control u star. Now let's solve few problems. Suppose that we are given a system, second order system is given to us. So consider the system x1 dot equals to 2x2. So we have a linear second order system minus 6x2, and we need to prove the system is asymptotically stable using Lyapunov theorem. बच्चे आजकल बदमाश हो गए नहीं पॉज लिया बच्चे आते हैं भागते हैं आते हैं भागते हैं आते हैं भागते हैं कोई कंसिस्टेंट नहीं होता है To prove the system to be asymptotically stable, we must need to start with a good Lyapunov function. So how can we start with a good Lyapunov function? So let's consider a positive definite Lyapunov function c1 x1 square plus c2 x2 square. And this c1 c2 we can determine by deriving the expression for derivative of v. Now in order to find the derivative of v, we know we can calculate it using the gradient and then x dot. So it is nothing but 2c1 x1 2x2 and then 2c2 x2 minus 5x1 minus 6x2. So this will give us 4c1 x1 x2 minus 10c2 x1 x2 and then 12c2 x2 square. Now since we need to prove the system is asymptotically stable, we need to show that the derivative of v along the system trajectory is negative definite, not only semi-definite but negative definite. So now the only thing that we can infer from here that if c1 equals to let's say 5 and if c2 is let's say 2, then v dot will be 20 c1 x1 x2 and 20 c2 x1 x2 minus 12 c2 x2 square. That means we will get derivative of v as some negative quantity x2 square. But from here we cannot say that v dot is negative definite, because for negative definite this v dot should be 0. It should be 0 at x1 0 and x2 0, not just x2 0 or not just x1 0. So we need to check this condition also. So from here the expression of v dot is minus 12 c2 x2 square. So that means v dot will be 0 at xt equals to 0 and we are free to choose any value of x1. So we cannot conclude from here that v dot is negative definite. For that, let's check when x2 is 0 and when x2 dot is 0, what is our x1 and x1 dot. So when x2 is 0 from here, when we put, that gives us x1 dot as 0. That means x1, when x2 is 0, x1 is some constant value. And now when we put x2 derivative as 0, that gives us 0 equals to minus 5x1 minus 0, because x2 is 0. So the only solution for x1 dot, x2 and x2 dot to be 0 is x1 and x1 dot as 0. So that means this v dot is negative definite. Therefore we conclude that the system is asymptotically stable, and the Lyapunov function that we have used is v equals to 5x1 square and 2x2 square. Okay. Okay, now let's check how to identify a class K functions. So we need to determine whether the following functions are functions are class K function or not. Okay. The first one is the function alpha r, which is given as tan inverse of r. Second function is r to the power c, where c is greater than 0. Third function is minimum of r square, and the fourth function is alpha r equals to 2r minus sine r. We need to determine whether these functions are belongs to class K function or not. Okay, from the definition of class K functions, we know that the function should be continuous over the defined domain, that is a positive domain, some 0 to a. So this alpha r should belong to continuous function defined over 0 included 0 to a, let's suppose, and it should give belong to positive real value. It should be 0 at 0, and it should be strictly increasing, strictly increasing. So we need a function need to satisfy these three conditions. Should map to a positive value, should be 0 at 0, and should be strictly increasing. So let's analyze each function one by one. So our first function, which is tan inverse of r, we know that this function is 0 at 0, so the first case is satisfied, and also over a positive domain 0 to a, it maps to a positive real number, so the second condition is also satisfied. And if we find its derivative, so if I find alpha dash r, that is derivative of alpha with respect to r, it gives us 1 by 1 plus r square, and this is also greater than 0. That means this function is strictly increasing. So yes, it belongs to class K function. This alpha r belongs to class K function. Our second function was so our second function is r to the power c, where c is greater than 0. So for a positive domain from 0 to a, this will give us a positive number, so it belongs to r plus, it maps to r plus. And also when r equals to 0, this is 0, and now its derivative is also greater than 0. That means it is strictly increasing, so it also belongs to class K function. The third function is a minimum of r and r square. Now here also we can check that when r equals to 0, the only solution is alpha equals to 0, because the minimum will be 0. And when we define the domain to be some 0 to a, that is some positive domain, the function will also map to positive value, so that condition is also satisfied. And its derivative, if we see, its derivative will also be either 1 or 2r, which is also no, yeah, which is also positive, so it is also strictly increasing. But one thing that we need to check is that if we plot our function alpha r, which is, let's plot this function, which is minimum of r and r square. So since we are interested only in the positive domain, that is from 0 to some domain a, let's say, so the function r is this linear function, and then we have the r square, which is a parabolic. Now the minimum of this will be this green function, and at this point, which is 1, we can see that at r equals to 1, this function is not differentiable. Okay, but even if the function is not differentiable, this function belongs to class K function, because differentiability is not the condition for a function to be of class K. The only thing that we need is that the function should be continuous over the defined domain. Okay, so that we need to remember, that we need only continuity. Differentiability is not needed. Differentiability is not needed. Now let's move on to our final function, which is 2r minus sine r. So this is also 0 at 0, and since r also, this is 2r, so it is always greater than sine r also, so it also positive. It maps to a positive quantity, and its derivative, if we check, it will be 2 minus cos r, 2 minus cos r. So since cos belongs to minus 1 to 1, so this quantity is also greater than 0, so it is also strictly increasing. That means this is also a class K function. So this is how we can check whether a given function belongs to class K or not. Now in the first question, we checked a linear system using Lyapunov theorem. We gave guarantee that the system is asymptotically stable or not. For the non-linear system, let's try the same thing, and for this case we have x1 dot as minus x1 cube minus 2x2, and x2 dot is x1 cube minus 4x2. For this system, we need to find the Lyapunov function for asymptotic stability. So the thing is, we know that the system is asymptotically stable. Now if we know that system is asymptotically stable, then there must exist a Lyapunov function whose derivative is negative definite. Okay, so this is also a theorem, that if the system is stable, then there must exist a Lyapunov function whose derivative is negative semi-definite. And if a system is asymptotically stable, then there must exist a Lyapunov function whose derivative is negative definite. So for that case, we need to find out the Lyapunov function that will render its derivative to be negative definite, such that this system is asymptotically stable. Okay, let's start with a general quadratic Lyapunov function, because we need to satisfy the condition of positive definiteness also for the Lyapunov function. So the easiest one is to start with a quadratic Lyapunov function. Since we have two states, we can start with c1x1 square plus c2x2 square. Now its derivative along the system trajectories is 2c1x1 and 2c2x2. Okay, sorry, x2 dot x2 dot. Now let's do the calculations. It is so the first term will give us a negative quantity, it is minus 2c1x1 4, and the last term also will give us a negative quantity, that is 8c2x2 square. But these middle terms are problematic because this gives us 4 c1 x1 x2, and then it gives us 2 c2 x1 cube x2. So these two terms are very helpful because these are negative, but these two terms are of sign indefinite because we don't know what is the nature of the state x2 or what is the sign of the state x2. Similarly, what is the sign of state x1 cube into x2. So these are sign indefinite terms. But since this should be negative definite, what we can do is that so here is x1 also. So let's consider this x1 x2 as common, so this will give us minus 2 c1, and then it will give us what, c2 x1 square. Now if we select c1 c2 such that this term vanishes, then what we will left with is the negative term that would make us the Lyapunov derivative to be negative definite. So let's consider c1 c2 in such a way that this term goes away using this coefficient to be 0. So that hints us to use c2 x1 square as 2c1. Okay, so let's consider c1 as 1. Then this c2 will be something like, or no, we should go the opposite way. Let's consider c2 as 1. Then this c1 it should be x1 square by 2. Now if we have such a scenario, then let's see what our p dot will be. Okay, so let's consider c1 as 1, so it is, no, c2 as 1 and c1 as x1 square by 2, so it will be x1 4 by 2 and c2 as x2 square. So this is also positive definite because it is always positive and it will be 0 only at x1 0 and x2 0. Now finding its derivative, we will have 4 x1 cube x1 dot divided by 2 plus 2 x2 x2 dot. Now let's put the derivative, so it is 2 x1 cube and x1 dot is minus x1 cube minus 2x2 and 2x2 cube minus 4x2. So it is minus 2 x1 6 minus 4 x1 cube x2 plus 2 x1 cube x2 minus 8 x2 square. So in order to make this term to be 4, we need to have 2 over here, 2 over here, so that would make us 4. So this will also be 4, and hence these two terms cancelled out, and this will make us 16. So we will be left with negative definite terms only. So this makes our system asymptotically stable. So the Lyapunov function that we need is, so this is V, this is V. So the Lyapunov function we need is x1 to the power 4 by 2 plus 2 x2 square. Remember that this is not unique. This is not the only Lyapunov function that will give us this result. Okay. We can also use function like x1 4 plus 4 x2 square. So that Lyapunov function will also give us a negative definite derivative of v. So there can exist many other positive definite functions that would give us the same result. So that basically depends on the design parameter. So that helps us in designing the parameters of the control u when we have a control problem and we are designing a control using Lyapunov. So based on the constraint of the actuators and all, we can choose that particular Lyapunov function to give some bounds on the control parameters. Okay, now let's consider that we have a scalar system which is given as x to the power 5 minus x, and it is given that its v dot satisfies minus x4. So we have a system whose derivative is minus x to the power 4. We need to find the Lyapunov function v. Alright, now since we are given dv by dt, so we are given dv by dt, which we know that we evaluate as quantity. Okay, now it is given to us, dv by dt is given to us. What we can do is that in order to find v, we can write by writing it as dv by dt and dx by dt. Okay, so this will give us the same relation. Now let's solve this. So dv by dt, it is given as minus x to the power 4, and dx by dt is given to us as x to the power 5 minus x. Now dv can be written by integrating. So since at x equals to 0, v should be 0, so this gives us nothing but v. Now in order to find this integrand, we can cancel x, so it will be x4 minus 1 dx. Now this integral we can easily solve by considering this as some variable p, so that will give us as some dp, and then we can solve it as log of p minus 1 by 4 dp. So that means v is given as minus 1 by 4 log of x to the power 4 minus 1. And obviously the argument of log should be positive, so we need to ensure that x to the power 4 is greater than 1. Now let's start with a time varying system and try to analyze the stability using Lyapunov theorem. So this would be question number 5. Okay, suppose that we are given this linear time varying system and we need to analyze the stability using the Lyapunov function or Lyapunov theorem. Okay, so let's analyze stability using Lyapunov theorem. Okay, let's start our most favorite quadratic Lyapunov function that we most of the cases use as this form of quadratic Lyapunov function. And if we find its derivative, it will be x1 dot and x2 dot. So by solving along the system trajectories, it could be, so this will give us minus x1 square minus x1 x2 plus x1 x2 and plus x2 e to the power minus t into x1. So from here we can see that we cannot comment on anything because we have the sign indefinite term x1 x2. Okay, so this Lyapunov function fails to give us any inference about this time varying system. So now let's change our Lyapunov function to something like so let's modify our Lyapunov function at some time varying Lyapunov function. So tv is a function of t and x. Okay, so this Lyapunov function, one can easily check that it is also positive definite because this is 0 only at 0 and it is also positive. So it is a positive definite Lyapunov function. Now let's calculate its derivative. So since it's a time varying function, its derivative we should analyze, we should find its derivative of t also. So that would give us, so for x1 it is x1 dot, and for another one we have x1 x1 square by 2 and then minus e to the power minus t and then x2 1 plus e to the power minus t x1. So x1 dot, it is minus x1 minus x2. This quantity is x1 square e to the power minus t by 2. This quantity is x1 x2 and plus x1 x2 e to the power minus t. Okay, now let's take everything which is common over here. So yeah, So this quantity is nothing but x1, x2, 1 plus e to the power minus t. That means it is minus x1 square 1 plus e to the power minus t and minus x1 x2 1 plus e to the power minus t for this term, and then this term is x1 x2 1 plus e to the power minus t and this negative term. So these two terms cancel each other. So what we have is, let's open it. So it is minus x1 square e to the power minus t and then minus x1 square e to the power minus t by 2. That would give us minus 3 by 2 x1 square e to the power minus t. Since this is a whole negative term, that means it is less than equal to minus x1 square. So what we started with, a positive definite function, will end up with v dot to be negative here. We cannot say it is negative definite unless we check the value of x2 when x1 is 0. So let's consider the point x1 as 0 and x1 dot is 0. At these points, when we have x1 as 0, that would give us x2 dot is 0, means in the manifold where x1 is 0, x2 is a constant one. Now from the first equation, since we have x1 dot is 0, that means this 0 equals to 0 and minus x2. So the only possible solution is x2 equals to 0. Okay, so since v dot is negative and it is 0 only at x1 0 and x2 0, that means our v dot is negative definite. So we can conclude that this time varying system is asymptotically stable. Okay. Okay, now let's consider our final problem. Okay, let's consider a scalar system given as x plus 2u, and it is given that at t equals to 0, it started at 0 and at some final time equals to 1 second, it should attain the value 2 such that it minimizes our cost function j, which is evaluated at over the time 0 to 1, and it should minimize the integral x square plus u square. So we have to find the optimal control. Okay, by looking at this optimal control problem, we can easily check that this is a constrained problem where we are given a cost function, and for all the time we need to satisfy this constraint that the state should be governed by this dynamical system for whole of the time period. So if that is the case, we need to find the Lagrangian. So the Lagrangian is nothing but this cost function, which is x square plus u square. And since it's a scalar problem, there would be only one Lagrange multiplier, so lambda times of the constraint. And the constraint over here is x square plus 2u minus x dot. The constraint let me write it. It is x plus 2u minus x dot should be 0. So this is our g. Now since we need to find the optimal control, so that we can easily calculate now using the Euler equation. So we need to minimize this Lagrangian with respect to control. So that solution is given as the Euler equation. So we need to minimize with respect to control. So we will solve Euler equation with respect to control only. So that is given as 2u minus 2u and plus 2 lambda. Yeah, since there is no u dot, so this whole term goes to 0, so it is 0. So the optimal control u star is nothing but minus of lambda star. Okay, now this solution is with respect to the Lagrange multiplier lambda. So that is not the closed form solution for u, because anyhow we need to solve for the solution of lambda. And how we can do that we can do. So the task now is to find the solution of lambda. So the task is solve lambda t, and that we can do by again solving the Euler equation with respect to the state x, and that is given as dl by dx is given as 2x and plus lambda and then x dot. So minus d by dt of respect to x dot, it is minus lambda. So this equals to 0. So it is 2x plus lambda dot equals to 0. So it is lambda dot equals to minus lambda minus 2x. Okay, so the lambda is governed using this dynamical equation. And when we solve the other Euler equation for the other variable, so we have evaluated Euler equation with respect to u, with respect to x, and we know that with respect to lambda it gives nothing but g equals to 0. That means our dynamical system. So the another equation is nothing but our constraint, which is x dot equals to x plus 2u, that is our system equation. So now we have three equations. We have equation of u, which should be minus lambda. We have the evolution of lambda and the constraint as the system dynamical equation. And initial condition and final condition, or the terminal condition of a state, is already given to us. That is, it should be 0 at the initial time and it should be 2 at time t equals to 1 second. Now since we have everything, we can easily solve this system to find the solution. So let's write everything down. So we have x dot. Now since u optimal is nothing but minus lambda, so x dot is given as x minus 2 lambda. So x dot is x minus 2 lambda, and lambda dot is, we have derived, it is minus lambda minus 2x. Now this is nothing but a linear second order system with given initial condition. So this equation we can solve. Now in order to solve, what we can do is that we have yes, the lambda value we can put over here. So when we calculate x double dot, it will be x dot minus 2 lambda dot, and and x dot we know it is x, no, let's keep it x dot only. Lambda dot we know it is minus lambda minus 2x, and lambda we know it is put lambda, it will be, yeah, okay, so it is x dot plus 2 lambda plus 4x. Now 2 lambda, it is nothing but equal to x minus x dot, so it is x minus x dot plus 4x. So x dot, these two things cancel out, equals to 5x. That is x double dot minus 5x equals to 0. And we can easily derive the solution for this uh, second order system by converting it to some exponential e to the power rt, and when we do so, that is, so our x dot is nothing but r square e to the power rt. So the solution brings down to finding r square minus 5 e to the power rt equals to 0, so that will give r equals to plus minus root 5. So our solution xt is nothing but c1 e to the power root 5t and c2 e to the power minus root 5t. Now since we have the solution of x, we can find the constant c1 and c2 by using these initial conditions. So here at t equals to 0 we know, that it should be 0, so that would give us c1 plus c2 equals to 0, and at t equals to 1 we have 2, so 2 equals to c1 e to the power root 5 minus c1 e to the power minus root 5. So from here we can calculate c1. So c1 will be nothing but 2 divided by e to the power root 5 minus e to the power minus root 5. And c2 is nothing but negative of this c1. When we put it over here, our solution xt is nothing but c1 e to the power root 5t minus e to the power minus root 5t. Or we can convert it into hyperbolic function. So the final expression for xt will be 2 sine h root 5t and divided by sine hyperbolic root 5. Now this gives us the expression of x. How can we solve the expression for lambda? So lambda is nothing but x dot minus x. So lambda is nothing but x minus x dot by 2. Since we have x, we can calculate x dot, and that would give us the expression for lambda. So lambda, when we calculate, it will be sine hyperbolic root 5t minus root 5 cos h root 5t and divided by sin h root 5. And u, the final expression for u will be nothing but minus lambda t. So this is our optimal control u star, which minimizes this cost function, that is integrand of x square plus u square, and derive our system from an initial state 0 to our final state 2 in time t equals to 2 seconds. So here what we have derived is the open loop control. by explicitly driving our expression of u, or if we kept lambda in terms of x, then that would be our closed loop solution. So this is how we can design, or we can find the expression for optimal control u star that minimizes the cost function and derives our state from an initial state to final state in some final time t, which in this case is 1 second. So that's all for today. We will discuss about discrete time system and related theories regarding observability, controllability, and observer design and controller design in the next week. So if you have any question, you can ask. Okay. Thank you for joining today's session. We will meet next week.